Hi students, welcome to our Super Physics channel, Physics Star. Okay, today let us discuss about how to apply law of conservation of angular momentum in case of rolling object. So usually, when do we apply law of conservation of angular momentum? As usual, when torque is zero. Yes or no? When torque becomes, or when the net torque acting on a system is zero, or on a rigid body is zero, then automatically angular momentum is conserved. Tau net is equal to 0 and it implies to delta L is equal to 0. Means L is equal to constant. That is what we call conservation of angular momentum, right? Now, how to apply that in case of rolling object? So here, in case of rolling object, uh, if you want to apply law of conservation of angular momentum, where to apply? I mean, with respect to which point we have to apply? Let us discuss by solving two problems. Okay. Yes. The problems are as follows. Now listen. See the 85th question, which is there in HC Verma actually. A solid sphere is set into motion on a rough horizontal surface with a linear speed v in the forward direction. In the forward direction, and an angular speed v by r in the anti-clockwise direction as is shown in the figure. Find the linear speed of the sphere when it stops rotating and B when slipping finally ceases and pure rolling starts. So this is an interesting question. See, usually when it is started to move in the initial stage, actually it is rotating in anti-clockwise direction and it is moving in the forward direction. Yes or no? It is moving in the forward direction. But after that, what is happening? Yes. But after that, what is happening? It is going. See, first, suppose if we take a sphere, if we just turn it in reverse and if we move it, if we just push it forward, if we turn it reverse and push it forward onto a floor, then what will happen initially? It turns like this and it moves forward, right? Okay, now same situation is there in 85th question. Okay. So, but angular speed is nothing but V by R only. Okay, so what happens for some time due to friction which is acting on that at the point of contact? Okay, the friction is acting at the point of contact, right? So because of that friction, it stops. Okay, it stops rotating after some time, and after that, what happens from that instant onwards when it stops rotating? Okay, now from that instant onwards, again it starts pure rolling in the forward direction. Yes or no? So that question, let us do it now. So first condition here, if we want to apply law of conservation of angular momentum, then with respect to what I have to apply? Just a minute, let me, okay. With respect to what I have to apply? Now with respect to point P, the point of contact, with respect to this point P, this is a point of contact. With respect to that point P, I'm going to apply law of conservation of angular momentum. How can you say? Why? Because with respect to that point P, okay, whatever the force which is acting there is completely means it suppose if the object is in pure rolling or if the object is in motion, definitely there will be only one force, that is friction. That's it. Either sometimes it supports the motion or sometimes it opposes the motion, right? In that case, the friction is passing through that point. Am I right or not? So, however, the torque produced due to friction is equal to 0 because it is passing through the axis of rotation itself. Am I right or not? So with respect to point P, there is no torque acting on it. Even if we even if we take mg, mg is also passing through point P only. But because of mg, it doesn't rotate, it doesn't roll. Okay, only because of either because of friction. Okay, the reason may be friction. That's it. But that friction is passing through that same point P. It means that with respect to P, if we calculate, then there is no torque at all. Okay, because the friction is passing through the point of contact P. If we consider the point of contact as that ICR, like instantaneous center of rotation, then there is no torque produced due to friction. Yes or no? So that's why. Now let us apply that principle here with respect to P, applying law of conservation of angular momentum with respect to what we are going to do with respect to point P. With respect to point P. Why? Because that friction is passing through that point P only. Hence, the torque produced due to friction is equal to 0. Hence, net torque is equal to 0. Hence, angular momentum is conserved with respect to that point P. Am I right or not? So, now let us take, initially it is rotating in anti-clockwise direction, right? If it is rotating in anti-clockwise direction, then torque produced due to that, angular momentum produced due to that omega will be opposite to that of angular momentum produced due to V. Yes or no? What is angular momentum produced due to V first? If we consider the translatory motion of that sphere, then it is moving with the velocity V, velocity of center of mass V. Then we can say the angular momentum with respect to point P as simply m v simply r. Why? Because perpendicular distance from point P is r, capital R. Am I right or not? Plus or minus? It is minus. Why minus? Because it is rotating in anti-clockwise direction. Here, this is angular mvr is angular momentum due to translatory motion, and v by r is omega is equal to v by r. With that, how to write the angular momentum here? That is I omega. Yes or no? I omega means it is solid sphere. See, it is solid sphere. Therefore, solid sphere means I, okay, I, it is what? I P into omega. I'm sorry, I C, right? I C into omega. With respect to center, we have to consider. With respect to center, we are considering. That's why I C into omega, which is equal to, now, after it is starting pure rolling, after some time it starts pure rolling, right? It means that the same sphere starts rolling in forward direction, rotating in forward direction like clockwise, and at the same time the velocity will be v only. Here omega will be v by r only. If omega is equal to v by r, then we can say that it is pure rolling, right? Like this, it is pure rolling. It means that at the bottom, this is velocity v, and this is rotational velocity, r omega, tangential velocity. So therefore, v is equal to r omega at this point P. Therefore, it will be in pure rolling. Am I right or not? So if we consider that situation, pure rolling condition, now how to apply the law of conservation of angular momentum, that is m into v into capital R plus, I'm sorry, when it travels like this, then its velocity changes, right? Its velocity changes. Consider it is omega dash, hence it is v dash. Means after coming into pure rolling, however, its translatory motion changes, right? Velocity changes, velocity of center of mass. Yes. So m into v dash R plus I value IC into omega dash. IC into omega dash. See, before situation, after situation. Before that, it was rotating in anti-clockwise direction and moving forward. Afterwards, it is in pure rolling condition. So in both the situations, we are applying law of conservation of angular momentum. Therefore, we are going to get mvr minus 2 by 5 mr square into omega value. We know it is v by r. It is given there, which is equal to m into v dash r plus 2 by 5 m r square into v dash by r, because it is in pure rolling condition. Therefore, r square gets cancelled. Here r, here square gets cancelled. Okay. So, and here also r on both sides get cancelled here. Here also gets cancelled. And also mass also gets cancelled. Now, let us write the remaining values. V minus 2v by 5 is equal to v dash plus 2v dash by 5. Okay. Now, if I simplify this, v minus 2v by 5 is what? 3v by 5, which is equal to 7v dash by 5. 5 gets cancelled. Therefore, that implies v dash is equal to 3v by 7. V dash is equal to what? It is 3v by 7. That's it. Now, what is he asking us to find? Velocity only, no? Find linear speed or linear speed of the sphere. We have calculated the linear speed of the sphere in which situation? When it stops rotating and when slipping finally ceases and pure rolling starts. Okay. When it stops rotating, we did not do. We have done B first. First we have done B. We have done here just this is B condition. This is a answer for the question B. Now for the question A, how to solve? When it stops rotating. When it stops rotating means what? Still it is in translatory motion only. Still it is in translatory motion only. See, let us write A here. When it stops rotating means what? See here, this is a sphere. Initially, it was like this. The angular velocity will be omega. And here, this is a velocity. And after some time, what happens? After some time, this omega will become 0, whereas its velocity changes. Why does it change? Because friction is acting there. That's why velocity will not be constant always. So therefore, we can say that all right, now listen. So therefore, we can say that in the initial situation already we have just calculated. What is at first? See here, V minus, see, just take from this one. V minus 2V by 5, because everything is same, right? In the first case only we have calculated MVR minus IC omega. MVR minus 2 by 5 MR square into V by R. That is the first case actually. Okay. So what am I doing? I'm just taking V minus 2V by 5. It is for first case. Directly we did. Yes or no? Or else write it clearly, because again it has to be cancelled out. MVR minus 2 by 5 into MR square into V by R, which is equal to. Okay, now let us apply for the second condition. In that, omega is equal to 0. That's why, okay, angular momentum due to rotation, we are not considering. Only due to translation, we are considering, that is m into v dash into r. Okay, mv dash into r. Again, as usual, RR gets cancelled, mass also gets cancelled. Hence, I can write V minus 2V by 5 is equal to V dash. That implies V dash is equal to what? 3V by 5. V dash is equal to 3V by 5. This is the answer for the first case. Is the answer for the first case. Understand? And now, let us do another problem here. Let us do another problem. See the second problem. A solid sphere. Let us try to copy it once more. Yes. Now let us do it now. 86th question. Okay. See the 86th question. Now the answer, now the diagram which is related to that 86th question. A solid sphere rolling on a rough horizontal surface with a linear speed v collides elastically with a fixed smooth vertical wall. Find the speed of the sphere after it has started pure rolling in the backward direction. So now listen, 86th question I am answering. 86th one. Solid sphere. There is a solid sphere which is rolling on a rough horizontal surface with a linear speed v. With a linear speed v means this is a solid sphere. This is rolling on a rough horizontal surface with a linear speed v. Rolling means definitely it is pure rolling only. Omega. Okay. With a linear speed v collides elastically with a fixed, rigid, smooth wall. This is wall, so that it comes and collides with this. Here, this wall is smooth. There is a lot of difference when the wall is rough and when the wall is smooth here. Okay. Now here the wall is smooth. Find the speed of the sphere after it has started pure rolling in the backward direction. See, what happens if it hits that wall after some time? Okay, after coming and hitting that wall, what happens? How does it move immediately uh, after the collision? Immediately after the collision with the wall, how does it move? If we observe it once, it is rolling in clockwise direction until it reaches the wall. Am I right or not? It is rolling in clockwise direction until it reaches the wall. So when it reaches to the wall like this, okay, if there is no such friction on the wall, then observe carefully. If there is no friction on the wall, then friction has to support that motion of it. I'm sorry, friction has to oppose the motion of it here. Means it should not rotate. Okay, now. Okay, now when it hits that wall, it should not rotate again. Am I right on it? It should not rotate continuously. Am I right or not? When there is a friction. But here there is no friction at all. So what happens? It continuously rotates in the same sense. Means suppose if it is rotating in clockwise direction, even after hitting the wall also it rotates in clockwise direction only. Keep one thing in mind, even after hitting the wall, after hitting the wall elastically, okay, the sphere rotates in the Same sense. Same sense means what? Before hitting, it was moving in clockwise direction. Means it was rotating in clockwise direction. Even after hitting also, it comes in backward direction only, but it rotates in clockwise direction. Means the situation will be like this. The situation will be like this. Observe carefully. See, this is after hitting. After hitting the wall and bouncing back from the wall. Omega will be same sense. Omega here clockwise, and even after hitting also it is clockwise. But velocity will be opposite. And it has the same magnitude of velocity. Why? Because already it is said that it is elastic collision. It is hitting elastically. Yes or no? It is hitting elastically. That's why it moves in the same. Velocity, magnitude of velocity will be same here. Now, what about third condition? Third condition, see here. Find the speed after the sphere. Okay, of the sphere after it has started pure rolling in the backward direction. Pure rolling in the backward direction. Actually, as soon as it hits the wall, it starts moving like this only. But after some time, what happens? The rotation stops, and from there onwards, it starts rolling purely. From there onwards, it moves. It will be in pure rolling condition. Means it is omega dash, and it is v dash. This is pure rolling. And what about this one? Just after hitting the wall. Now what we need to calculate? Find the speed of the sphere. Means v dash value. Here v dash value we need to calculate. Same situation. Even here also we have to apply law of conservation of angular momentum with respect to that point P which is in contact with the surface. See here, this is that point P which is in contact with the surface. So what am I going to do? I'm going to apply law of conservation of angular momentum with respect to point P, because no torque, there's no external torque. Am I right? So in this situation, now I need not to take the first case. Let us take the second and third case. This is the second case and this is the third case. B and C. This is the first case. Let us take. So in B and C, I'm applying law of conservation of angular momentum. How to apply here? Applying law of conservation of angular momentum. Now, for B, let us apply. That is m into, okay, V into R minus MVR minus I value. It is a solid sphere, right? Is this a solid sphere? Yes, it is a solid sphere. So I value is 2 by 5 mr square. 2 by 5 mr square into omega value. Here already before that, it was in pure rolling only. Before that, it was in pure rolling. Yes. Clearly, it is mentioned a solid sphere rolling on a rough horizontal surface. Once observe the question. Rolling means pure rolling only. Okay. So therefore, omega value also I can apply it as V by R, no problem at all, which is equal to. Now apply the same conservation of angular momentum at C now. Let us find out the angular momentum at C now. How to find that? Again, m into V dash into R plus 2 by 5 m into mr square into what is omega dash? V dash by R, because it is in pure rolling condition, right? So therefore R square gets cancelled. Here also R square gets cancelled. And both sides R is there. That's why again R gets cancelled. M gets cancelled. So what are the remaining values? V minus 2v by 5 is equal to v dash plus 2v dash by 5. Yes or no? Now let us send this, let us solve this. Actually, 3v by 5 is equal to 7v dash by 5. Therefore, v dash is equal to 3v by 7. V dash is equal to 3v by 7. Same as before one. Yes or no? This is the answer. Okay. So this is about how to apply law of conservation of angular momentum in case of rolling object. Okay. So keep on watching my videos so that you'll get a good conceptual understanding. I mean, you'll get a good conceptual knowledge as well as uh, you'll get a few tricks how to solve the problems. Okay. Keep watching. Please like, share, and subscribe to my channel, Physics Star. Thank you.